Hello, my name is Sam Kurtzinger, and welcome to Lab 4, Oscillations. The purpose of this lab is to predict the motion of a weight on a spring as it oscillates. First, we are going to track a video of a spring oscillating in a program called Tracker. Using the initial conditions determined in Tracker, we will then make a model of this motion using vidle. Finally, we will compare the data from the video to the motion of our model in Python. You will see that by applying just a couple fundamental principles of physics, we can accurately predict a spring's motion. First, let's go over the two main principles at work here: Newton's second law and the energy principle. Newton's second law predicts the changing velocity of the spring as it oscillates. The energy principle is the total change in energy set equal to the change in kinetic energy plus the change in potential energy, which we break down into gravitational and spring components. Observe the video being tracked in Tracker. I used a calibration stick to calibrate the length of the spring and set the coordinate system origin where the spring is connected to the wall. After Tracker collected all the data, I took the x and y coordinates seen here and placed them in an Excel file to be read by my video code. Here's the first part of my code. The ball's mass is represented by ball.m. The initial position, which we got from Tracker, is set equal to ball.pos, and the ball's initial velocity is set to 0, and time starts at 0. The CSV data from Tracker is taken in by these three lines of code, and G, the gravitational constant, is represented by 9.8 here. The spring constant is represented by K sub s, and the relaxed length of the spring is set equal to L0. S represents the difference in length of the spring from its relaxed length. These three equations calculate the kinetic, gravitational potential, and spring potential energies, respectively. The kinetic energy formula is 1/2 mass times velocity squared. The gravitational potential energy formula is mass times g, which is 9.8, times the height. And the spring potential is 1/2 times the spring constant, K sub s, times the displacement squared. These three formulas translate into my lines of code here. On the left, you can see all of the forces being calculated. The velocity is updated with Newton's second law, and the position is being updated. These last lines of code update the energy changes, which we have represented by the formulas. Here's the code running. The red ball is the data from Tracker. Notice that the model does a pretty good job of predicting the motion. The red line is the spring potential energy, the green is the gravitational potential energy, the yellow, notice that it's 0, is the total energy of the system, and the blue is the kinetic energy. Now for the what does it mean questions. First, is the energy principle satisfied? The answer is yes. When we saw the model earlier, we saw that the yellow line was equal to 0. But the gravitational and the spring potential energies were changing. As one went up, the other went down, and vice versa. So, the energy principle was definitely satisfied. Question 2. Here are the two oscillations of x and y graphed. The periods of oscillation are very close, but when we analyzed the video, we saw that the x oscillation period is just a bit longer. Thank you for watching, and that concludes Lab 4.